Next, very very important derivation asked in the exam. So again, this will be asked for 10 marks. Okay. Derive expression for resonance frequency of practical parallel resonance circuit where capacitance as well as inductance both having internal resistance. So both the branches I told no in the ideal we have parallel RLC, three branches will be there. In the practical resonance circuit, parallel resonance circuit, only two branches will be there, L and C. First practical circuit is only L is having internal resistance R, and second parallel one is capacitance branch is also having internal resistance. So let us having two coils here. Inductance is having internal resistance of RL, capacitor branch is having internal resistance of RC. So RC belongs to the capacitor branch, RL belongs to the inductance branch. It's connected to voltage V with variable frequency. So you have to vary the frequency. And vary the frequency, the reactance of the L and C is going to vary. So we have to vary until resonance occurs. Now let us derive expression for this. First branch, let us, I told know the procedure. First find out in this branch what is the impedance of the branch inductance branch. RL plus JXL. RL plus JXL is the impedance. XL is omega L, and admittance is given by reciprocal of that. So YL is equal to 1 by ZL, 1 by RL plus J omega L. So again, in how we did, we have to rationalize. We have to separate real part and imaginary part. So in the denominator plus is there. So we have to multiply with minus 1 by RL plus J omega L into RL minus J omega L, RL minus J omega L. So 1 into RL minus J omega L is same RL minus J omega L. This is in the form of A plus B into A minus B. A plus B into A minus B is nothing but RL square minus J omega L whole square. A plus B into A minus B is A square minus B square. This is A plus B, A minus B. It is equal to A square minus B square. This is RL square. Okay. This is omega L whole square. Omega square L square. This is J square. But J square is minus 1. But J square is minus 1. Minus 1 into minus 1 is plus. J square is minus 1. If J square is minus 1, you'll get minus will this J square is minus 1, no? So minus 1 into minus is plus. We'll get plus. So we can separate it as RL by RL square plus omega square L square. That is the real part. And imaginary part is minus J omega L by RL square plus omega square L square. Similarly, here we have two branches now. So consider impedance of the branch containing RC. That is the capacitance branch path. We have to find out what is impedance. Impedance in the capacitance branch is RC resistance and minus JXC. For capacitance, you have to write minus JXC, and where XC is 1 over omega C. Where XC is 1 over omega C. And admittance of the branch is actually reciprocal of ZC. So RC minus JXC. So this is in the denominator we have imaginary part. So we have to rationalize it. Here minus is there because we have capacitance. So once you rationalize, you have to multiply with plus. Because of minus, for rationalizing, you have to multiply with 10. RC minus J omega C into RC instead of minus plus J omega C denominator also RC plus J omega. That so that this value will not change. If you divide this by this, you will get 1 only. Okay. RC minus J omega C, RC plus J omega C. Then multiply RC J omega C with 1, you will get numerator the same term. But in the denominator, we will get again A minus B into A plus B. A minus B into A plus B is, again this formula we are using again and again, A square minus B square. A value is RC square, B value is J omega C whole square. Here J square is there, no? J square is minus 1. So minus 1 into minus 1 is plus. We will get plus RC plus J omega C, RC square you'll get plus here, omega c square, omega square c square. Now we have yc as this and yl as this. You have to, that is individual parallel inductance branch total admittance is this, capacitance branch admittance is this. Now total admittance is given by adding both. Y is given by inductance branch, capacitance branch, both admittance you have to add. In both the cases we did rationalization. We got real part and imaginary part. Even in the capacitance branch also real part and imaginary part. So you have to add both. This is from equation number 1. This is from equation number 2. Okay. So you can call this as equation number 1 if you want. Or from there only you can. You have to add these two to get total admittance of the circuit. Now we have separate this real part and imaginary part, RL by RL square omega square L square. Similarly, here also real part is RC by RC square plus omega square C squared. So real part and real part separately and add it. You will get total real part. And here also imaginary part is there. Here also imaginary part is there. So plus j you take common. Plus j you take common. Then you left with 1 by omega c. 1 by omega c by r square rc square plus omega rc square plus omega square c squared minus j we already taken. So minus omega l by rl square omega square L square. Okay. So in any problem related to the practical resonance circuit, first find out total admittance in the parallel circuit. After that, at resonance, the imaginary part should be 0. This part should be 0. So total susception should be 0. So at resonance, equate this part to 0. At resonance, equate this imaginary part j, coefficient of j, this entire part you have to make it as 0. So and omega should be replaced with omega r. So you write here, wherever omega is there, you write omega r, 1 by omega rc by rc square plus omega r square c square minus omega rl rl square plus omega r square L square. If you equate this, bring this minus to right side is equal to, then here you have to look carefully. Left side you have 1 by omega rc square 1 by omega r square c square. Right side we have omega rl by rl square plus omega rl square L square. Next you have to cross multiply. You have to cross multiply. You multiply with this, multiply with this. Okay, 1 by omega rc, 1 by omega rc into rl square plus omega r square c L square. This multiplied with this multiplied with this. After that, this L you have to divide throughout by L. You will get like this, and this omega r you have to multiply here. This omega r you bring here. This omega r cross multiply and bring here. It becomes omega r square. This L you bring left side. This you bring it to left side. This is a product, no? Divide throughout by L, multiply throughout by omega r. Multiply throughout omega r, this will get cancelled. You will get omega r square. Divide throughout by L will give you L here, and here L will get cancelled. So 1 by LC RL square plus omega r square L square is equal to omega r whole square RC square plus omega r square C squared. Next, here we have RL square by LC, this multiplied by this, again this omega r squared L squared by LC. Here also you have to multiply omega r square RC squared omega r squared by C squared. This will get cancelled, and here this L will get cancelled. Here we have RL squared by LC omega r squared by L by C omega r squared RC squared, here 1 by C squared. Next, RL squared by LC, you have to take omega r one side. Here omega r is there, here also omega r is there. So you have to take omega r one side only. So this 1 by c squared you have to bring left side. This you bring, this plus becomes minus 1 by c squared. And this if you bring it to right side, minus omega r square by LC. And now right side you take omega r square common. Right side you take omega r square common. So you left with rc squared minus LC. RC squared minus LC. So first we got this term R squared, RC squared minus LC if I take omega R. So left side also you should get the same term here. Here you have to get same term RC squared by 1 by LC only you have to get. So what you have to take common? RC squared is there. So you have to take 1 by LC common. 1 by LC if you take common, you left with RL squared, and C is already there. C is already there. So only one C you have to write here. And in the denominator, in the numerator, actually there is no L. There is no L here. So you can write L here. So what you can do is you write one L here, here also one L. Okay, one extra step if you want, you can write here also L, and here also L. And if you take LC common, if you take LC common in the denominator, we left with this C. L we already taken. We left with C here and here L. So see that this RC squared minus LC, this also some RL squared minus LC, minus LC minus L by C minus L by C, same type you should get here also. So after that, omega r square is equal to this much is equal to this entire thing divided by this, entire thing divided by this. So divide throughout by RC squared minus 1 by LC. So already 1 by LC is there, this much, and this divided by RC squared. So omega r square is 1 by LC. We are dividing throughout by RC square by LC. Okay, we left with 1 by LC, root of RL square minus L by C, RC square minus L by C. And omega r is equal to root of this full entire root of this, root of 1 by LC, root of RL square minus L by C, RC square minus L by C. So this derivation is very, very important. This will give you 10 marks. So to remember, omega r is actually 1 by root LC. That is, in case of parallel resonance circuit, omega r is 1 over root of LC. We have additional term here. That is RL square minus L by C. In the denominator, RC squared minus L by C. Okay. And FR is given by omega r is 2 pi FR. Omega r is 2 pi FR. So FR is 1 over 2 pi root LC. So if both inductance and capacitance does not have any internal resistance, RC and RL will 0. Internal resistance of coil is 0. Internal resistance of capacitance branch is also 0. If RL and RC are 0, 0, this part is going to be, we left with this root of 1 is 1. We left with only 1 over 2 pi LC, which is same as resonance frequency without having any internal resistance. If any resistance is there, we have additional term, numerator inductor part RL square minus L by C, in the denominator part RC squared by minus L by C. So this is in hertz, this is in radians per second. So next, some conditions, this additional part. Suppose what happens if RL and RC both equal to root of LC. Okay, if RL and RC is equal to root of LC, then RL square is root of LC whole square is L by C. L by C minus L by C will get 0. Will get 0 by 0. Okay, omega r is equal to 1 over root LC. You left with 0 by 0. So this is actually infinity. So that infinity means the circuit will resonate for all the frequencies. Irrespective value, if the value of R and L, if you take it is equal to root of LC, for all the frequencies, circuit will resonate. Circuit will resonate for all frequencies. Sometimes they will ask for the exam also, they are going to ask. This is the admittance. You can stop here only. No need. You can stop here. These are additional part. These are total admittance. Only circuit behaves as purely admittance. Only this part. Y is equal at resonance. Y is equal to only this much. And current is given by IR is equal to E into YR. You can stop at this point. To here you have to write, you'll get 10 marks.